And welcome back, everyone. We're going to be continuing with Simplex 2D Noise Implementation Part 2.
Right. The first part we need to deal with right now is getting our hash gradient indices for each of our simplex corners. So we'll calculate out some more variables. This will be II, which will be the value of I masked with 255. Just like in the other noises, this is to make sure that the value that we save in II is in the range of 0 to 255, because the way we calculate, we know that in our permutation table, while we have 512 values, we're relying on the fact that there's 256 different values repeated twice. But when we're querying the our permutation table, we're using the X and Y, both querying the permutation table, taking the number it returns and adding them together. So as long as each one of them is less than 255, we'll never exceed the 512 bounds of our permutation table. So that's why we're doing that, in case anybody missed it from our other videos. So, and I ramble, so let's get back to coding. So var JJ is going to be the result of J masked with 255. And we'll get a couple of gradients. This will be our gradient index 0 is going to be the result of what we find at our permutation table at element II plus permutation table JJ. It's got more than 5 letters.
I know, I'm not going to say anything.
And we're going to take the modulus of 12 because we're looking for our a gradient, and our gradient table only has 12 elements in it. So we're using the modulus to make sure that we don't go above that. So if I duplicate that and change that to GI1 and GI2, GI1 is going to be II plus the value of I1 plus prim table JJ plus J1. And if you remember back up here, we're using I1 and J1 to calculate our
Which simplex
simplex we're in. So we're using those numbers to help pick out what index we're using based off of our simplex that we're in. So, and here we will use +1 and then JJ +1, all modulus of 12. So this will give us our 3 indices that we're going to use. Now we need to calculate our 3 corners, the noise contribution for each one. So we're going to make a T0 variable that is going to help calculate the value of our noise at this corner. So we're going to take x0, square it. So instead of using squared or math power x0 to the power of 2, we're just going to multiply it by itself because it's faster. And we're going to do the same thing with 0, and I'll go back and fix this other one. All right, so that gets us started. We're going to check that number and determine whether or not it's less than 0. If for some reason this number turns out to be less than 0, our contribution from this corner will be 0. Else, we've got some more calculations to do. We're going to take our value of T0, and we're going to square it. So we're going to multiply it by itself. And then noise 0 is going to equal T0 squared again
Noise equals T0.
Well, that was supposed to be N0. Apparently I hit NO. N0.
Okay.
There. And this is going to be multiplied by the vector2 dot product of the vector that we get out from our grad3 table given the GI0, or grad index, that we calculated above. And we're going to make a new vector2, and this will be the vector of x0 by y0. So that will be the contribution of our first corner. Now the nice thing is, our other two corners are pretty much the same thing. So we can copy and paste that twice more. We have to make some changes. So we need to change T0 to T1, X0 to X1, X0 to X1 again. Same with the Y1s. T1, N1, T1, GI1, X1, X1, and down here we change these to B2. So that takes care of all of those. Now, the last part of it is to return a number. Now, we're going to massage it a little bit to make sure that what we return is going to be in the -1 to 1 number domain. So we're going to take the value of 70 float, and we're going to multiply that by the sum of n0 plus n1 plus n2. Build it, make sure that there's no errors. So no errors there. Let's go to Game Manager. And I don't want to do iterations at this moment. Let's change I to a value of 1. Let's duplicate this noise line, paste it, come out the previous one, and change this to be Simplex. And it's 2D, we don't have a third component, so that takes care of that. And if we run it and hit play, we get gray. So if we look, and I'm going to set this to 2 just to make sure that we don't have the same problem with Perlin, but I don't think that's it, because this one shouldn't exhibit that same problem that Perlin noise does. Yeah, so I've missed something. So back in the Simplex noise. You want to pause it, and then we'll go through a code and figure out where the problem is?
Okie dokie, here we go. Okay, and we're back. Lee, I'll hand it over to you.
All right, yeah, one of those golden rules, if you're going to use a constant and you're going to calculate stuff out, make sure you calculate using the right order of precedence. So, if you do your division before you do the subtraction like you're supposed to because the order of precedence says so, you end up with the wrong number. So where I had 2.7, I should have had this much, much smaller number. So this is what happens when you code on the fly. So if we change this guy out.
By the way, if we lose power or something, I'm just letting everyone know. Yeah, we've got a pretty big storm brewing outside. Hey, what do you know?
Now we got noise. Also, look at the time.
Very fast noise.
Yeah, very fast noise. Now, we can have some fun with this. We're not animating it because this is not a 3D noise.
Right.
But one of the things that we can demonstrate is, if we go back over to our game manager, is we can temporarily bring in the iterations again.
Mm-hmm.
So if I bring in... No, before I even bring in the iterations, I want to show something else. One of the problems that we had with Perlin 2D and, again, the 1D is if we had divided by 1 or where we had whole numbers, we ended up with that even grid or the middle line gray. So we had no random noise in it. It was just solid gray. With simplex noise, if we try to simulate those same conditions, we don't have that problem. So that's one of the nice things about simplex, just one of a couple of different things. So now if I go back over and then bring in our octaves or multiple iterations, that means we can do I from 1 instead of I from 2 up to 8. As opposed to what we were doing before to compensate for that problem inside of Perlin. So if we take a look at this one, we get a nice little cloud texture that looks a lot like what Perlin did. There's a little bit more contrast. If you were to look at this and Perlin side by side, you'd notice that like this, it looks a lot closer to value noise as opposed or in terms of contrast, as opposed to Perlin, which seems a little bit more uniform, a little bit more washed out. But unlike value noise, if we go back to a single iteration and we check I and set it to 32, where we get that
grid.
Right, where we get that grid or blurred grid, depending on how we were looking at value noise. And Perlin had that nice organic feel to it. We'll find that if we use those same values again inside of here with an I set of 32, we get a gradient organic look. But again, it looks different than Perlin. It's a little bit higher contrast. We've got a little bit tighter cell definition than we had before. But this is a hallmark of different noises. Every noise has its own look. And this is how simplex looks.
Awesome.
So, and let's compare the 8 octaves again. So, because now we have each of those different noises. So I can duplicate this line. And I'm going to duplicate it 2 more times. First one will be value, then Perlin, and then simplex. And we're going to do 8 iterations of each. So here's 8 iterations. The nice thing is, even though Perlin will give us uniform gray at an I of 1, it still has to run all those calculations, so the speed will be the same. And that's what I want to compare and contrast here, is the speed for 8 iterations of noise for each of the 2D textures. So if I run this one.
Man, my math is just broke tonight.
What's that?
I was just looking at 8 iterations, but I was looking at the number that you had and the less than symbol, but I'm the last person to ask anything dealing with
Well,
math.
you completely lost me. Well, the 8 octaves, 8 iterations, the less than sign, what were you looking at?
Oh, I was just thinking, well, you're multiplying I by 2, 2 to the 8. So this is going to give you 8 or 7.
2 to the 8th should give me 256. So to get to 258, you start off with I of 1, then 2, then 4, then 8, 16, followed by 32, by 64, by 128, 8 octaves.
Okay, groovy. Thanks for holding my hand.
No problem.
It's late.
Well, you got me to the point where I started questioning myself. No, I'm pretty sure. Let me count that out just to be, but I'm never wrong. So.
Oh, okay. Well, there you go.
Yeah, right. All right, but now that I understand what you were asking, let's jump back over here again. Our speed for 8 octaves, verified 8 octaves now, is about 24, 25, 26 milliseconds. So we'll call it 25 milliseconds. Well, it's hanging out at 24. We'll give it benefit of doubt, 24.
Okay.
So 24 milliseconds for value noise. Eight octaves of Perlin.
$38.
38, 39. So definitely slower. And then back over here. And let's look at Simplex.
And about 31.
So 31, 32. So it looks like Simplex has got the upper hand on this one.
Simplex? You mean value?
No, this is Simplex. Well, what was... Oh, Simplex
24.
was... 24. Okay, yeah, that's right. So Simplex is faster. That's right. Simplex will be faster because it's...
value will be faster.
I'll get it right. Eventually, value is faster in 2D. Simplex will be faster in 3D. But we're getting, what was it, 31, 32
in Simplex.
For Simplex? Yeah, I'll get it right. Let's go back to Simplex real quick. And what I want to do is copy those values that we were using before we switched over to the constants. So let's put the square root operations back in and see what those do to our calculation times.
Oh, yeah, I mean, that's just a given.
Oops. So,
especially with square root in there.
So it added about 3 milliseconds?
About 4, actually.
4? Okay, so about 4 milliseconds. But that's only a 128 by 128. So it's an exponential as your texture size goes up. So if we were to go back and we change up here, so we're quadrupling the size. So if it's a true linear relation, 4 times 4 would be 16 milliseconds slower. So let's see what we get. So we're at 143, 141. So average about 142.
Yeah, sure.
All right, so we'll call that 142. Now let's jump back over. Back to simplex noise. We'll undo these changes. So if it's a true linear relation, then we should have a 16 millisecond difference. Now I'm curious to see what we end up with.
127, 128, 27. We'll go with 128.
Okay. Which works out to be how much?
Oh, you're asking math now. Don't ask me.
Oh, well,
I don't care if it's simple.
I thought you were writing down notes.
Well, you're talking, we went from 31 up to 128 with this one.
Right.
And the other one was around,
well, that was 128, so you gotta like undo and redo.
and what was the other one? 36 up to 142, I think. Yeah, 140.
141. So about 12, 14.
Not much.
Yeah. So it's pretty much a linear.
This computer is awesome.
Yeah. So you're basically getting roughly.
But you said a full second or two? Wow.
Yeah, well, I got this slow computer too. I don't have 6 cores turning away, going all out.
What are you talking about? We're not using 6 cores right now for doing this.
Well, you're still running a lot faster than mine. Yeah, we put multi-threading in. Weren't you paying attention?
Oh, okay, I see. That was when I was refilling my popcorn container.
When you were still trying to figure out the greater than.
Well, that was the problem. My brain just didn't want to figure it out. I was like, oh, gosh. It's easier just to ask.
Yeah. But
man, it's like 11:15 at night, and I'm about to wrap up with you and shift gears and have to go over to Nelson Land into ASP.NET. What a day.
But, any way you look at it, where you're doing needless calculations that can be turned.
Oh, I completely agree.
Into a constant.
Absolutely. There's no reason to do the extra calculations.
Yep. Even if it is only saving us between 4 and 16, and that goes up as our texture size goes up. Right. But in a video game,
we're looking for every cycle that we can save.
16 milliseconds is forever. So
very cool. Okay, so then that pretty much wraps up the implementation of the Simplex 2D noise, right?
Of the 2D, yes, it does. So I'm going to put some things back to where they were for when we come in the next video for our 3D implementation of Simplex.
Okay. So. Is that everything?
Well, yeah.
I didn't know if there was anything else you wanted to adjust.
No. That's all I want to adjust for this one. So
awesome.
We should get to go right in the 3D version when we come back.
Alrighty. Well, everyone, thank you very much, and that concludes this video.